This is a solution of sodium bicarbonate mixed with a little bit of phenol red indicator. I used this briefly for a demonstration that I didn't really like too much. Because I didn't like it, I was left with this bottle of solution. I'm going to use it up now on the demonstration that I don't like very much. Here's a beaker with 100 milliliters of this solution and a thermometer. Now I'm adding a scoop of solid calcium chloride. As the salt dissolves, there is a color change because the pH is lowered. There is also a slight temperature increase. Some solid is formed and there's an evolution of gas. Yay! How exciting! I mean, it's not that bad. It's just not something I thought was worth doing often enough. By the way, the temperature increased very rapidly. A whole 2.7 degrees Celsius. Really exciting. There's about 550 milliliters of this stuff left, and it's not going back on the shelf. I know a similar reaction happens with aluminum sulfate, and I'm going to try a few other salts that might give a reaction. In my mind, using it up in experiments is better than just dumping it. We'll start with a scoop of aluminum sulfate. There's some evolution of gas, but no color change. I need to add another scoop, I think. Here we are a few seconds later. That's a little better. This level of excitement is why I didn't really do too much with this reaction. It's great for teaching reactions in general, but not nearly showy enough to win people over to study chemistry. The color change is a little bit more pronounced on the spoon, but to call a reaction on a spoon exciting, something needs to burn. One of the first chemicals I ever got was magnesium sulfate. There's a little left in this bottle from almost 25 years ago. I wouldn't mind using this up either. Well, this is even less exciting than the other ones. I have an idea. Dump in a bunch more and see what happens. A whole lot of nothing. Surely there must be a reason for this. I'm not telling though. You explain it in the comments below. Next up, some zinc sulfate. Well, this one's a little more interesting. We've got a nice reaction, a nice color change, and a lot of bubbles. We can also see at the bottom a precipitate is starting to collect. The three-layer effect is actually somewhat attractive. I like that. We might have a winner with this reaction. The first reaction was with calcium chloride. Let's see how calcium nitrate works. The problem with calcium nitrate is that it has a tendency to clump up and become rather brick-like in storage. This is clearly reacting, but very slowly as the chunks try to dissolve. After a few seconds of nothing happening, I decided to add a few more chunks of calcium nitrate. It doesn't seem to help much, but the reaction is definitely going. I'm bored, so I'm moving on. Next. The last one I'm going to try is aluminum potassium sulfate, since the aluminum sulfate gave some reaction. Even without stirring, you can see that there's an immediate reaction. This is somewhat on par with the zinc sulfate, and isn't as painfully boring as some of the other ones. Perhaps you noticed, but I stopped measuring the temperatures a long time ago. None of them, this one included, were even slightly warmer to the touch. But at least this was something to look at for a change. So I'm down to the last 50 milliliters of the sodium bicarbonate phenol red solution. And what's this I have on the right? It's a mixture of the ones that actually gave a decent reaction. Calcium chloride, aluminum sulfate, zinc sulfate, and aluminum potassium sulfate. I'm hoping that by dissolving at least some of each of them before mixing will help the reaction along. So, let's see what happens. All right, now we're talking. There's a very small chance I'll ever mix up the solution again, but I feel like now I know the reaction I'd use as a demonstration if I did. This mixture of salts in a saturated solution. This actually borders on spectacular, especially when you look at how the different regions have different colors. What started a long time ago as a potential new demonstration and ended up being an annoying chemical solution taking up space has been used up in a way that ended up teaching me something. The demonstration I wanted to do wasn't good enough for a show, but with some honestly random experimentation, I have refined it to a point I can use it. It's also worth noting that the calcium nitrate is finally reacting. It's the third beaker from the right. It took a while, but the reaction is finally in progress and chugging along nicely. Which presents a nice opportunity. Since the bubbles are actively forming, I thought I'd do a quick test to show that it's carbon dioxide that's being given off in these reactions. With any luck, this match will be extinguished as it goes into the CO2-rich atmosphere inside the beaker. And it was. I also wanted to highlight the final state of the beaker with the mixed salts. The unevenness of the reaction produced a really interesting pattern of color in the bubbles. And speaking of the bubbles, they're rather tenacious. In a previous video, I did a cerium-catalyzed Belousov-Zhabotinsky reaction that was supposed to oscillate in 4 colors. I tried a fresh solution of malonic acid potassium bromide, but still didn't get it to work right. I said if I had enough malonic acid, I'd try it again with fresh potassium bromate solution too. Well, that's what I'm doing. The potassium bromate solution was recently microwaved to get it to dissolve, so it's still a bit warm. Unfortunately, there's still no telltale amber bromine color when the potassium bromate and malonic acid potassium bromide solutions were first mixed. This doesn't bode well for the rest of the reaction, but I'll keep going anyway. The next steps are to add the cerium ammonium nitrate sulfuric acid solution and ferroin indicator. Once the indicator is added, it does start to change colors. It goes through several different color changes and it does oscillate. Unfortunately, the reaction still isn't working right, and I'm not sure why. There's supposed to be a red color during one of the changes. It never happens. Each 100 milliliter trial uses just over 3 grams of malonic acid, and I'm down to about 2.5. Maybe I'll revisit this another time when I get more malonic acid, but for now, it's no good, and I just have no idea why. While we're on the subject of previous videos, here are the nice pale green crystals of iron 2 chloride I recovered about 2 weeks ago. Clearly, they're not doing so well. Eventually, I'll try some other tricks to reduce the iron 3 chloride to iron 2 chloride. That will be in an upcoming video, probably this spring. The last follow-up is from the chemiluminescence video. I used a commercial solution to produce a glow, and it wasn't as bright or long-lasting as it should have been. The remaining 400 milliliters of the solution had to go, so why not do 2 larger-scale demonstrations? Here are 200 milliliters of the luminol containing solution and 200 milliliters of potassium ferrocyanide solution. I shut off the lights and mixed them together. There was not even the faintest glow. I used the rest and tried again. Nothing. They've been sitting on the shelf for 4 years and still worked a little. In the month or so since I filmed that video, the luminol solution has completely spoiled. Okay, back to using stuff up. I've got a little bit of table sugar left that expired from kitchen use a very long time ago. It's about to be digested in a spectacular fashion. This stylish mug will be its last stand. In the oscillating reactions video, I used some concentrated sulfuric acid that had bits of dissolved cap in it. This is that acid. As you can see, the cap has seen better days. It was left over from an experiment where it was ever so slightly contaminated with some salt water. This is its perfect end too. The demonstration is about as simple as it gets. All you have to do is dump the acid into the sugar and stir it up until it liquefies. Normally you use about the same volume of sugar and the same volume of acid, but here I'm just using these things up, so there's actually a little bit excess acid. Don't worry, I'll move in a minute. When working with a concentrated acid, my attention is on not getting it all over the place rather than on hand placement in relation to the camera. Anyway, it has to be stirred for about a minute or so. The molecular formula for sucrose is C12H22O11, meaning that there's a nice ratio of hydrogen to oxygen. Sulfuric acid really likes water, and it's pulling it right out of the sugar molecule, leaving the carbon behind. As you stir, it feels a bit like stirring wet sand until all of a sudden it liquefies. When that happens, stand back. It's very smoky, it gets very hot, and you don't want to be anywhere near this thing. The smell is not entirely unpleasant until the aerosolized acid starts eating your lungs. Do this outside or with plenty of ventilation. As simple as the reaction is, I don't get to do it very often. It's a real pain to clean up after. The fluffy carbon product has to be soaked in a sodium bicarbonate solution for about an hour, but it floats, so it has to be continually poked. It's also not too easy on the glassware. This stylish mug is now cracked right across the bottom. My project to clean up the chemical storage room is ongoing. You could say it's a new state of mind. But getting rid of all this has made a big difference. I've also gotten some practice making and editing videos, and they're starting to suck a little less. I have a lot of chemicals that are still good, but they're just sitting on the shelves. That's about to change. In the next video, I'll introduce you to my plan for doing more with my chemical inventory than just looking at it. I enjoy learning about chemistry, and I enjoy sharing what I've learned with others. I hope you'll join me in the learning process. Thanks a lot for watching, and I'll see you next time. Happy New Year!